Chapter 9 deals with electrons and atoms in the periodic table. This is a couple chapters thrown into one. So, if we look at the periodic table, and well, I guess that's what we're going for, is the periodic table, but are there other elements as reactive as hydrogen? Hydrogen is a pretty reactive element. And we look at other elements just below hydrogen in the periodic table, and then we see uh, some elements that are very, very unreactive, like the noble gases. So, what's going on with this? We've talked a little bit about Mendeleev and periodic law and how he was able to place certain elements together and show that certain properties reoccur periodically. And we have since further combined this with quantum mechanics to better understand what's going on. And we're going to talk about two models today, Bohr model and the quantum mechanical model, that show the importance of how the periodic law actually works. And periodic law is a generality. It's not, there are exceptions to it, and the truth is much more complicated than what we're talking about in this class. But the quantum mechanical model, at least as far as we know, is the most accurate to describe it. Perhaps in the future, like some version of string theory might supplant it, but right now, quantum mechanics is very good at describing what's going on in the atomic world. One of the major problems with the quantum mechanical model, though, is that we can't use quantum mechanics to explain macroscopic events like gravitation and things like relativity combined with gravitation. So we don't have the combination of that. The quantum mechanics can describe things in a very small level, things like protons, neutrons, and electrons and atoms and small molecules. We haven't been able to build up to very large systems like star systems from this, though. So that is a problem with our physics. But right now, the quantum mechanical model works extremely well and perfectly as well as we can see. So some people that are important here, Niels Bohr and Erwin Schrödinger, also with Albert Einstein, not listed in here, played very big roles in the development of quantum mechanics. And they were pretty shaken by their own discoveries. It was kind of a weird time, interesting time to be in science. And some of this, as I explained, it may seem kind of weird. So let's start with light. Light is a form of electromagnetic radiation. So what does that mean? So there are four fundamental forces of physics. So gravity, electrostatic, sometimes called electromagnetic, nuclear weak, and nuclear strong. It turns out the nuclear weak force is in fact electromagnetic, so you can argue there's three forces. Some people consider dark energy to be a force, so you'll hear the forces sometimes called 3, 4, or 5. So that's up to debate. Electromagnetic energy deals with the second force, and also photons. Photons are quanta that, so quanta means little tiny packets of existence that carry the electromagnetic force. And so light, for instance, is a form of that, and electromagnetic radiation, light in the smallest units are photons, and they carry this force. And light is not matter. There are certain things that describe matter, but light is a form of energy, and there are certain things that are a consequence, because light is energy and matter is not energy, although matter and energy are interchangeable by approximately equals mc squared. But certain things, matter, for instance, has structure. At least atomic matter has structure. Light itself does not have structure. In fact, in a single point, you can overlap as much light as you want. There will be no problems with that. But of course, there is a problem to do that with matter. That is not able to do. And light is energy. It moves. Well, we already covered this. Moves through space at 3 times 10 to the 8 meters a second, and this is known as the speed of light. So another thing that's interesting about light does not experience time. So light is an interesting thing that there is no time when it comes to light itself does not experience time. But we, of course, we do experience time. So I, sorry, I like talking about the fun stuff here. And the idea, though, the universe exists in small packets of existence, and we call these packets of existence, we call them quanta. Well, for space-time itself, we call it the Planck length. So between 2 points, if you draw in the air, point A, point B, and you put your finger line through that, and how many points are between that line, there are not an infinite number of points. So the universe exists in set specific places that it exists and where it doesn't exist. And these small graduations, they're called quanta. And simple proof for that is, well, if there was an infinite number of points between point A and B, it takes a finite amount of time, it would take forever to get anywhere. So from that, there is not an infinite number of space between 2 points. Space itself exists in only discrete, individualized quanta. So that is where we're coming into, that there are specific steps in quanta that exist for many things, and it kind of breaks our understanding, right? So this is some of the things I'm talking about there. That's probably why when you hear about how Bohr, Schrodinger, and Einstein were like, what is going on here? So when they started to figure this out, like, this is weird. So yes, prepare to have your mind blown. After this lecture, I don't know if you're going to listen to it all the way through. It's going to be a little long one. Think about it for a bit, maybe listen to it again, and let it sink in. Once it sinks in, it'll make more sense. So light can also be a wave. This is what's weird about light. Light can be observed as both a wave and a particle. It depends on how you observe it. Will it behave like a particle? So light can be described as a wave, and the way it's described as a wave is actually it's an oscillating magnetic and electronic field. So when you study physics, you can learn more about that. But the electronic field, as a photon is moving forward in space, the electronic field oscillates and the magnetic field oscillates, and they also oscillate perpendicular to each other. So in 3 dimensions right now, so here you can see the red wavelength there. So that's parallel to the screen. Coming out diagonally, like coming out perpendicular to the screen, would be either, if one is magnetic, the other one would be electronic, and then they would oscillate that way. And this is also known as a transverse wave, which means the displacement is perpendicular to motion. So sound is a longitudinal wave. That means that the displacement is parallel to the direction of the wave. This is a transverse wave. This is perpendicular. Ocean waves are transverse waves as well. So displacement, when you're in the ocean and the wave comes, you go up and down, and the wave moves perpendicular to where your motion is. So this is a transverse wave. And the wavelength, we describe it can be from peak to peak, valley to valley, or 0 to 0, the full peak to valley kind of thing. So however you want to describe the wavelength. But the wavelength, and then we give it the Greek symbol lowercase lambda, is what we do to describe how long the wave is. So we'll go into the electromagnetic spectrum, but white light, so produced by a sun like the star, or star like our sun, or a light bulb, is actually a combination of light. And then it is also in the visible region. Visible meaning what we humans can see it. And you can take that white light and you can break it into its constituent parts. And red light with a wavelength of about 750 nanometers, so that's the length of the wave there. So 750 nanometers. I can see down to about 800 nanometers. It's hard to see 800 nanometers though. It looks kind of like really like dark brick red. And I can see to about 380 nanometers. It looks kind of like really light lavender. But most people, like I think most people can see that far, but it's really hard to see outside of about 700 nanometers for red and 400 nanometers for violet. Uh, Point of information: violet is different than purple. Purple is actually the combination of red and blue together. Violet is a specific wavelength of light, and so this is visible light, the ones that we can see, and so red is the longest wavelength of visible light, and violet is the shortest wavelength. And actually, Newton came up with this, the Roy G. Biv colors, and he wanted to have an extra one there. If you're wondering what indigo looks like, if you have a pair of blue jeans, that's the color of indigo. Indigo is that kind of dark blue, the color of blue jeans. It's dyed by the plant indigo. So if you're wondering what the heck color is indigo, it is that color there. But it goes red to orange to yellow to green to blue, indigo and violet, and that goes from long wavelength in red to short wavelength in violet. Although we humans, we are not spectrometers. We actually see red, green, and blue. We have our light-sensitive cones in our cells, red, green, and blue, and we interpret colors by the relative strength of those signals in our brain. So we see green the best, and red and blue less so, but green gives us the strongest signal to our brains. But we interpret a photon of energy by it'd be photons, because a photon would absorb a single cone. We interpret the colors based off of the relative amount of signals to our brain and our occipital lobe of our brain. So we're not as good at discerning colors as a spectrometer. We're pretty good. We're better than most biological creatures. Manna shrimp are better than we are, but they also don't have the big brain, so we have a big brain and we can appreciate it better. Manna shrimp do have better discernment, but they don't have the processing power and intelligence to discern it. But we are pretty good. We're better than pretty much all mammals. So if you look at a red shirt, for instance, it's red because it reflects red light and absorbs the other colors. So our eyes see the reflected light, and it makes the shirt appear red. And also, like I mentioned before, it's also the way our brains interpret the color coming in. So besides wavelength, we also have frequency, and that looks like V, but it's the Greek symbol nu. It's the lowercase nu. And for whatever reason, we in chemistry, we use lambda for wavelength and nu for frequency. And frequency just means the number for each second. And they're also inversely related because, remember, speed of light is constant. So something that has a very long wavelength is going to have a low frequency. And if something has a very low wavelength, it's going to have a very high frequency. So, and that's because the wavelength times the frequency is equal to the speed, and that's just a basic understanding. It's how far you go and how many times you do it. That's how far you go, and that's the speed of light. So, since the speed of light doesn't change, these values are going to be proportional. So let's look at the electromagnetic spectrum, and we start over here on the left on low energy, and we have radio waves. Then we move to the higher energy or shorter wavelength. Then to microwaves. Then we have infrared. Then we have visible, with red being the low energy and high wavelength, and violet being the high energy and low wavelength. Then we have ultraviolet. Then we have X-rays, then we have gamma rays. So why is it high energy? Well, if you see like imagine you're in a boat in the ocean and you have these long rolling waves, and then you're like, okay, I can just kind of sit back and I can kind of ride these waves out. Imagine if you had a bunch of waves coming at you on the far right end, where you have these really these crested things coming right at you, like which one is going to hit you harder. I think you understand that the higher frequency waves are going to carry more energy. That kind of, I'm hoping that would be intuitive to you, that the frequency, the higher the frequency, the higher the energy of whatever it is, the carrier. And in the case, it makes sense with ocean waves, it's going to be the same thing with photons. So it's an electromagnetic radiation. So each of these things, different types of parts of the spectrum do things. Radio waves, what radio waves do is they affect the orientation of magnets, especially on the atomic level. So it changes the way that the magnets of the nuclei and atoms arrange themselves. And these are very low energy waves, and they go for it's very easy for them to go very far. And we use these generally for communication. And we can also use these for MRIs. If you've ever had an MRI, the way an MRI works, they're actually it's nuclear magnetic resonance imaging. So when we said, well, we're going to do a nuclear magnetic resonance image for you, and people are like, I don't like the word nuclear. And so what they did was they dropped the word nuclear, and we called them MRIs, magnetic resonance imagers. So now we're like, oh, okay, I can go on that. And MRIs are completely safe. They use radio waves, and radio waves are not harmful at all. And they image you based off of hydrogen. They scan radio waves over hydrogens, and they can determine where the hydrogen is in your body, not only what type of hydrogen, but kind of the state it is and the density of it. And from that, we can determine like, oh, this is blood, this is muscle tissue, this is tendon, and this is bone. And then we can get a 3D image of your body. So that's what radio waves do. What microwaves do is they make molecules rotate. So microwaves, we also use these for communication. It's what radar uses, even though you think radar would use radio waves, because the R actually is radio waves. Radar actually uses microwaves. And someone working on a radar station, he carried chocolate bars in his pocket. And he noticed that when the radar was on, the chocolate would melt in his pocket. He said, you know what? I could use this to heat food. And so that person also went on to invent and market the microwave oven. And microwaves make molecules rotate. And then by molecular collision, the rotation energy turns into translational energy, which is temperature. So that's how microwave ovens work. Infrared radiation, and look at the word infrared. It means less than red, so lower than red. What infrared does is it makes molecules vibrate. So also increases energy. So and you can feel infrared radiation. It feels the same as heat. So if you put your hands in front of a fire and feel the heat, you're feeling the infrared light. And I'm using the word light. Typically, infrared light, visible light, and ultraviolet light is considered light. So the rest we call just radiation or its own names. But what the infrared light is doing is it's making the molecule, if you're putting your hands in front of the fire, it's making the molecules vibrate in your hands. And then the vibration energy by molecular collision transfers it to temperature. So invisible light, already mentioned, what visible light does is it causes electrons to jump up and down in energy. So red light's going to be small transitions, violet light's going to be very big. Ultraviolet light, so ultraviolet means beyond violet, so higher energy than violet. And what ultraviolet radiation does is it takes electrons on the outside of the atoms and or molecules, and it ejects them. So ultraviolet radiation, X-rays, and gamma rays, these are also known as ionizing radiation. So ionizing radiation is radiation that forms ions. How does it form ions? It rips off electrons. So these are the dangerous forms of radiation. So the other forms of radiation, at least by themselves, they are not as dangerous. Yeah, of course, if you give someone enough infrared light or microwaves, the person can cook, right? But I mean, it is not, people are worried about cancer, especially with cell phones. Cell phones use microwaves to communicate. Microwaves do not cause cancer. So you need to have ultraviolet X-rays or gamma rays to be able to cause cancer. And of course, ultraviolet radiation is the leading cause of skin cancer, for instance. So ultraviolet ionizes electrons on the outside of the atom. X-rays ionize on the outside and on the inside, so they can penetrate further into the electron cloud. And gamma rays they can also ionize electrons, but they also deal with the nuclei. So we will talk about electrons in this chapter, but when we talk about nuclear chemistry, the same rules apply. Orbitals, that kind of thing. Same rules apply for protons and neutrons, and gamma rays function just like visible light do for electrons. Gamma rays deal with transitions of protons and neutrons in the nucleus of the atom. So this is the entire electromagnetic spectrum, and let's move on. So I've already mentioned all of these here. So X-rays, we are familiar with them because of their medical use. We use them to image bones, typically, for instance. And X-rays are dangerous. Ultraviolet light, although we humans, we are slightly photosynthetic. We can, from a region of the spectrum called UVB, we can turn cholesterol into calciferol, which is provitamin D. So we can then store that in our livers typically, and then we can convert it into vitamin D that we use in our bones. So we are slightly photosynthetic. That's why we like to sit out in the sun, because it feels good sometimes. We do have part of our reward, like you get endorphin boosts from sitting out in the sun. But be careful, because too much UVB radiation is leading causes of skin cancer. Visible light, we've mentioned this before, it does not damage biological molecules. Visible light is safe. Well, I mean, if you concentrate enough, like if you shoot a laser at someone, yes, you can, if there's enough energy in it, but just from a regular light bulb or flashlight, it's not going to damage you. And infrared light, same idea. This makes your molecules vibrate. And I didn't know about night vision. You can use this to see in the dark, but we humans don't see infrared light very well. At enough intensity you could, because our eyes do focus infrared light into our retinas. So at a high enough concentration, you could see infrared light, but it would be very faint and hard to see. And the problem, it could also, if it's strong enough, it could damage your eyes. This is a problem. I've worked with lasers, and if it's an infrared laser, you can't, below 800, it's pretty much you can't see. But at 800, you can see it. Like I said, it looks kind of a brick red color. But it's really bright. It doesn't look bright, but it's really bright, and if you're not careful, it can damage your eyes. But most of us don't deal with lasers. So infrared photography, like here, and these are false colors. So it's not a real color, it's a false color. The James Webb Space Telescope, for instance, is an infrared telescope, and so when you see images from the James Webb, you're actually seeing a false color, kind of like the one here on the right here, the infrared photograph. So I already mentioned microwaves. We use them for radar, microwave ovens, and even low energy. And then radio waves, we use these for communication. The physical effect they have on on matter, they deal with the magnetic moments of nuclei and even electrons. So photons, and this is a weird thing. We can describe light as a wave, and we can also describe light as a particle, and it depends on how we look at it. And this is the thing that we didn't entirely understand. Einstein, for instance, he got his Nobel Prize for what's called the photoelectric effect. He didn't get it for relativity. Relativity was way too controversial at the time. He did not get rewarded for that. And it was also controversial because uh, how could this German Jew supplant our wonderful Isaac Newton Englishman describing the physics of the world? So Einstein was and still is extremely controversial, especially in Europe. In the United States, he was adored and loved, and he moved here, and we still adore and love him to the day. So it's kind of funny how things are. So he was not, and some people still don't consider him. Our Europeans are not very happy about him, but the smallest, like kind of called the smallest unit of an element is an atom. The smallest unit of light or electromagnetic radiation is a photon, and the practical part of this is it carries the electrostatic force. So it's like this one little packet of existence that carries the force of electromagnetism. And the how much energy this photon carries depends on the wavelength and or frequency, because they're once you know one, you know the other. So already aforementioned, the higher frequency means higher energy, and we have both wave-like and par-like properties. And already mentioned all these things, so you can read them. So range the three types of electromagnetic radiation: visible light, X-rays, or microwaves, or is increasing wavelength, frequency, and energy. So wavelength, so increasing low to high. So let's see here. Microwave is going to be the lowest, then visible light will be medium, and X-rays. Low order of increase. I'm sorry, I have this backwards. X-ray is going to have the smallest wavelength, then visible, then the microwaves. So microwaves are going to have the longest frequency. Low frequency is going to be microwaves, then visible in the middle, then X-rays is going to have high frequency. Energy is going to be the same as frequency. It's microwaves have the lowest frequency, lowest energy, lowest frequency. Visible in this case are the medium. X-rays is going to be the highest. So we can also use radiation to treat for cancer, and I already mentioned ionizing, and they can cause physiological harm to cells, and so they can use ionizing radiation to kill cells such as tumors. And so we can shoot beams at them, and then we can destroy them. And the problem is there's going to be a little bit of damage to the surrounding tissues, and it can cause various effects. But it's one way we can reach something without the use of surgery. So it is one way where you don't have to cut someone open and then deal with the consequences of infection. Of course, there's still issues with this type of treatment because if you have these dead cells and your body has to flush them out, and then there are issues dealing with your own immune system attacking and destroying that area. So it is non-invasive because of surgery, but then there's still a physiological effect, and it's still not fun. It's not like, hey, I get a free pass, I'll just get blasted with radiation. There are going to be some negative effects, but the question is with a question of risks versus rewards. So that's always something, and you have to, if you do have cancer, and I hope you don't get cancer, but this is something you have to deal with your medical practitioner to go over the risks versus the rewards of the various treatment options. But this is an option, and personally, I would take it over surgery. So emission inspection of elements. So when you excite atoms, they emit certain colors. And although, remember, we humans, we are not spectrometers, but we kind of see all of the light put together, and our brain interprets the signals coming from our eyes. But neon for us looks red, and the other gas that's there in the tube, it's probably oxygen by its color. It could be argon. It's hard to say from the picture. But that's the neon lights. There's only one neon light, and that's red. So the other colors come from other elements. So, oh, it's mercury. I was wrong. I'm sorry. So the only thing about mercury is it also emits in the ultraviolet. So, oh, you gotta be careful with that. So the light emitting from the tube, the mercury, it appears blue, but it also, like I said, it emits in the ultraviolet. So you got to be careful with mercury. And then the hydrogen. So the hydrogen is a pink one. So it's a very it's a pretty kind of, well, I don't know, light fuchsia pink. It's hard to describe. You have to see with your own eyes. The textbook doesn't do it justice. So let's talk about different types of spectra. So here is white light, like the light coming from the sun, for instance, and this is known as a continuous spectra. And then you can put it through a prism. And if you see here, here are the light coming from hydrogen, and then below that is helium. And then you look at this in neon, you're like, wait a second, I thought it looked red. Remember, our eyes are not spectrometers. Our brains just interpret the signal. We're kind of like, hey, can we eat this, or is it going to eat us? Or is this something we're going to form a social relationship with? And that's kind of what our brains are geared towards. We're not trying to discern electron energy levels when we see something. So we have to make very quick decisions and perceptions about things. So that's why we are the way that we are. But each of these lines here, though, and from these you can see, first of all, they almost look like fingerprints. It's like, well, fingerprints are unique for each person. These are now like fingerprints for elements. The other thing is, each of these lines, these correspond to energy levels. So where you have specific energy levels, they correspond to specific energy transitions in electrons. And so from this, we can use this information to figure out what's in stuff. So here is a picture of how a spectrometer works. You use a prism, and it bends the light, and then it separates it out. Bohr came along, and he came along with the idea like, hey, atoms are kind of layered. They're kind of like onions, and we have different shells, and then electrons populate these shells, and they go to higher shells. And from this, described many things, including the spectra of hydrogen. So understanding how the different energy levels go up and down. And it kind of looks like orbits of planets, but they're not really orbiting. So actually electrons just kind of occupy an area. So they're not necessarily buzzing around moving. They kind of just occupy a certain space. So, and then Bohr went ahead and then described the different energy levels, and it keeps on going up a ladder. And the top of the ladder is when an electron just rips off. And he went ahead and gave it a quantum number n, and n are positive whole numbers, and each of these energy levels are fixed or quantized. So, and they only exist in these areas. Think of it like an elevator, right? You go from one floor to the other. Although I know that, the elevator kind of follows continuous mathematics. In the Bohr model, the elevator does not stop between the floors, okay? There is nothing that exists between the floors. Not true. There is actually virtual particles. Sorry, that's the truth coming out again. But that's something that's beyond this course. So, but for this course, this is true. So how does then light happen with emission? Okay, so let's pretend that I am an extremely wealthy person, and I've invited you over to watch an amazing program on a television set. And in the front of the TV is this wonderful, relaxing, lazy boy that when you sit down, you can put your feet up and you can be so low energy, it's so soft, you could easily just fall asleep in that chair. Behind it is a couch. It's pretty comfortable, but it's not the lazy boy. Behind that is a wooden chair, which is, all right. But, in order to sit in it, you have to activate your stomach muscles a little bit, and you have to kind of, put a little bit of effort into sitting. And then behind that is a place where you can stand. And then behind that is a door where you can just be thrown out of the party. So what do you do? And so I'm the host, and I get there first. And I, of course, like a good host I am, I sit in the lazy boy. And I'm sitting there. I am very relaxed. And then suddenly I have to get up and go to the bathroom. And as I get up to leave, what's going to happen? Well, someone's going to go and steal the seat, right? And what happens when you steal the seat? There's a relaxation. They go, I can rest my back. I'm tired of standing. I'm tired of being in the chair. I'm tired of the couch. And of course, when the person coming from the standing position to the lazy boy, that person is going to relax harder than the person on the chair, than the person on the couch. And then, okay, so then let's compare that to the quantum mechanical model. The Bohr model. So the Bohr model here, electrons, the lowest energy level is the one closest to the nucleus. That's the very comfortable chair. And so when an electron is excited, so that means I've been sitting there for a while and I'm excited, I get up and then I move to the couch. So it takes energy for me to remove myself from the lazy boy to the couch. It takes energy for me to move to other places. So that's excitation, because it takes energy to move you up. And then when you go down in the energy, you will relax. And so let's see here. So it takes energy to excite up. And how can you get that energy? Energy can come from a chemical reaction. It can come from light. So those are ways that the energy comes from. And then when you relax, so when electrons relax, they emit photons. So where that relaxation and that change in energy of the relaxation, that corresponds to a specific wavelength of light. And for really big jumps, it can be even an ultraviolet. It can be a violet or ultraviolet. For really small jumps, it can be red, or it can be even infrared. So I know I told you that these deal with electronic transitions, but there's some leeway. There is a little bit of room here. Now, what about ionizing radiation? Ionizing radiation, so I told you there's a door in the back and their standing room. If a UV photon, for instance, would take someone from the back standing of the party and could push that person out the door, ejecting that electron from the atom. That's what an ultraviolet photon does. Ejects electrons on the outside to out into space. And if there is a stronger X-ray or gamma ray, that photon can take someone sitting closer. It can push out the person on the outside. It can do that, but it has enough energy that it can pick the person off of the lazy boy and toss that person in the front yard. So it can penetrate further into the atom. So that's kind of an analogy for how the energy levels work. But since these energy levels are quantized, they're set, and from that, since these energy levels are set, and then that means the energy differences between the levels are set, that means there's only specific types of light and colors of light that can be emitted. And from that, and since each element has a different nucleus, a different charged center, we can tell the identity of the elements by the light that they emit. So I've mentioned this before, so all these things here. And we can give numbers to them. For instance, the line, the 486 nanometers, that goes from the fourth quanta to the second quanta. Likewise, the 657 nanometers can go from the third to the second quanta. The n equals 3, n equals 2. So here then are the various numbers here. And with the ones going down to the n equals 1 level for the hydrogen atom, these are all ultraviolet. We can't see them, but we can see the visible lines there as such there. And you can see the bigger the step, the more violet the color. And the Bohr model is great for predicting lines of the hydrogen atom, but it didn't do as well with elements other than hydrogen or hydrogen-like. What does hydrogen-like means? It means it has one electron. So you rip off all the electrons at one, and the Bohr model works very well. So what we did is we built up the quantum mechanical model of the atom, and we went in a little further and showed things, and there are some finer points of quantum mechanics, and one of them is the idea of uncertainty. So when you have a particle, you can only so far be able to predict where its position and its momentum is. And so it's not like atoms and electrons are orbiting. They kind of occupy a certain space. At least their magnetic and electronic fields occupy a certain space. And it's not that the electrons are moving, it's all those places at once. So here is an idea, kind of like when the strike zone, you're playing baseball, someone throws to the strike zone, you're kind of looking to see the right place in that. And here's an example of the strike zone that the pitcher is going to try and hit that area as much as it can, but to a certain region outside that is the percentage of where the electron is. And now this is kind of, although this is trying to describe an electron using large objects like a baseball, the electron actually is in all those places at once. It's not just moving around, zipping around. It is not moving around. It is, like I said, the electron, and it's a weird particle. It will just sort of, it's at least the things that matter. The electronic and magnetic field will occupy that area, and it's different strengths at different areas of the of its orbital, and the orbital is the region that we're talking about, and there's shapes to orbital. So let's start in talking about the quantum mechanical model, and this is how we build it up. So we're going to describe quantum mechanical model, quantum numbers, and then we will build them up. You might want to watch this a few times if you're confused. Like I said, this is where things get confusing. We're going to start with the first quantum number. It is the principal quantum number n. And this is the lowest this is the lowest quantum number, and n exists as whole numbers. And the lowest energy orbital is the 1s orbital. And the s, it denotes an orbital. The S does not stand for spherical. It actually stands for sharp. And it's talking about the types of things coming from the spectra. So S is sharp. So the most hydrogen atoms at this temperature is the 1s orbital, and it's the ground state. So the ground state means the lowest energy level. And if you excite electrons in the hydrogen atom or any atom, you can go to an excited state. So that has extra energy. And then there's only one ground state, though. Ground state is the lowest energy state, and then there's many, many excited states. So starting with n, then the principal quantum number, and then as you increase energy, you can go into the higher quantum numbers, the higher n's. And then there is the L, the angular momentum quantum number, and this exists in from minus n integer steps through 0 to positive n. Okay, so for n equals 1, L can only be 0. When L is 0, that's an s orbital, comes from sharp. When n is 2, L can be -1, 0, or 1, and that denotes a p orbital, and that means for principal. When n is 3, L can be, it can be, I'm sorry, I was describing magnetic quantum number. Sorry, when n is 2, L can be 0 or 1. When n is 2, when n is 3, L can be 0, 1, or 2, and so on. So we'll see if we build up all the way to the quantum mechanical model. And again, people think S means spherical. It doesn't mean spherical. It means sharp. So, but this is an old spectroscopy term, and it's even older than me. So, much older than me actually. S is sharp, P is principal, D is diffuse, and F is fine. So you can study the quantum mechanical model even further, but the probability of finding an electron, it's like I said, it exists there. It's not moving around. It's where the electron exists, and it has density. We even say the word electron density. So it's where the density of the electron is in that, and it's more likely to be found in a certain distance. So it depends on the electron. It's found typically in a certain region. It's the lower quantum numbers tend to be close to the nucleus, and the higher quantum numbers tend to be further away. Actually, another fun fact: electrons can actually be in the nucleus of the atom. Something you learn in class, like, oh, the electron cloud is outside the nucleus. For the 1s orbital, there is quite a bit of electron density inside the nucleus of an atom. So that's something that's weird, right? You can learn today in class that the electron cloud actually is inside the nucleus of an atom. It's a small amount, but it does exist. You can put more massive particles like muons instead of electrons to form muonic atoms, and then more of the muon will be found in the nucleus of the atom. So we've studied muonic atoms to do that, but that's kind of above and beyond this class. So we can represent orbitals as geometric shapes. So this is true. The s orbitals tend to be spheres, and it is usually where it says, but 90% of the time, it's an area that it occupies, and it responds to stimulus too. So it just depends. And we can look at some of the shapes though. So for instance, here you have the spherical shape. For the 1s orbital though, it kind of will form almost like a three-dimensional donut kind of a shell. It doesn't really just hang out in the nucleus near the origin. There is a small amount of it in the nucleus, but not very much. It's kind of hangs out a little distance away, and there's the shape. So when I see the shape, though, I mean, understand the electron has a magnetic field, has an electronic field, so it kind of pushes, and it exists, and you find it by its field. It's not very massive, so gravity doesn't. It does have gravity, but the gravity is pretty much negligible. And it's where an electron lets itself be known is in its electronic and magnetic properties. So when I see this, I think of it more of where the electronic properties are of the atom. So when we have the different quantum numbers, so the principal quantum number, there can only be the subshell, and because the angular momentum, the L quantum number, it has to be 0. So n equals 1, you can only have 0. If n equals 2, the L can be 0 or 1, and when it's 3, it can be 0, 1, or 2, and 4, it could be 0, 1, 2, or 3. And then for each of these L's, so for 0, there's only one possible orbital. And then the next one, you can have 3 orbitals. For L equals for L equals 1, it could be -1, 0, or 1. For L equals 2, it could be -2, -1, 0, 1, or 2. And for 3, it can be -3, -2, -1, 0, 1, 2, 3, 4. So that means there's 1 orbital for S, 3 orbitals for P, 5 for D, and 7 for F. And then with the periodic table, though, each orbital can hold 2 electrons. And then there's the last quantum number we call the spin, which has to do with its with the orientation of the magnetic field of the electron at any given time. If they're equal opposite, then 2 electrons can occupy the same space at the same time, provided that their magnetic fields are opposite. So, all right, so we have the 1s orbital. Now we have the 2s orbital. It's higher energy, and because of that, it is a little more diffuse, and it's larger. So still, it's the electrons. These are all the same electrons, and all electrons in the cosmos are the same. There's not any difference between electrons. And with the electrons here, when it's in a 1s orbital, it's going to have a probability density like that. And then for a 2s orbital, it's going to be slightly bigger. And not shown here, there's actually kind of 2 regions where it kind of hangs out the most in. So then now we have the p orbitals, and they orient themselves along the axes. So x, y, and z. So we have 3 p orbitals, and they orient themselves that way. And the math for this is pretty complex. One of the things to note, though, the 1s orbital, it does not have a node. Node means an area of 0 density at the origin. So whereas p orbitals do, and all of them except for the s orbitals do, so the p orbitals do not really have any electron density in the nucleus. The s orbitals do, especially the 1s orbital. So the p orbitals they are pretty well, they don't interact as much with the nucleus of the atom, and they don't do. There's not as much funky chemistry with them. It's the s orbitals that cause the trouble. If you go on and study quantum mechanics a little more in depth, the s orbitals are the ones that especially for isotopes, can cause some issues. So what do we do when it's the third principal quantum number? Now we have d orbitals, and where this is going up, it's how we build up the periodic table. The p orbitals are so the s orbitals are the first 2 columns. The 3 p orbitals are the 6 blocks in that are the far right, and now the d orbitals. This is the transition metals. So, and with that, another aside, the bonding, although the bonding tends to go to noble gases, the d orbitals. There are various things that are more stable for the D shell, and it's just the bonding rules. We'll talk about general trends, but they're not always true for things with the transition elements, and even less so for the rare earths. So when you get the f orbitals involved. So here are the d orbitals, and how do you get these? And all of these images you get by there's various ways. One of the ways is that you can kind of look at the probability map from the distance, and you integrate that up. So you do some calculus, and you get these different shapes. So for the d orbitals, 3 of them are in between the axes, and 2 of them are within the axes. So the dx squared minus y squared and the dz squared. These orbitals lie along the axes. These are the ones that tend to bond. Those 2 on the far right. These are the ones that tend to bond. The other orbitals, they can bond, but they tend not to. Under certain circumstances, they can, but they tend not to. So I know I'm sorry if I'm going making this really confusing, but both the quantum mechanical model and the Bohr models can predict the spectrum for hydrogen. But the quantum mechanics, we can go even further than the Bohr model. And now, because of this, we've replaced the Bohr model with a quantum mechanical model. So Bohr model is still useful, still valid, but it only describes, the model only works under certain circumstances. So that's one of the things with that. And quantum mechanics can go even further. We can describe molecules, which are groups of atoms, where Bohr definitely cannot do that. Bohr model cannot do that. So how do we occupy electrons and give the configuration? So each orbital can only hold 2 electrons, but there are 1 orbital for the s's, and then there are 3 orbitals for the p's, 5 for the d's, and 7 for the f's. And it does go on further. You can go G, H, and so on, but we've only really named these ones, the sharp, principal, diffuse, and fine. Those are the only ones we've named. So hydrogen, though, we can describe as the 1s, the orbital 1s. The principal quantum number n is 1 there. The angular momentum is the s. That's the where that exists. And then the 1, the superscript, tells us how many electrons are in that orbital. So we can then give the spin. And what is the spin? It's already aforementioned. It is the direction of the magnetic field of the electron at any given time. So if you have an electron and it's this kind of this area this piece of matter that occupies this space that has a magnetic and electronic field, at any given moment the magnetic field generally points in one direction. That is called, but if you put another electron in there, the same idea, but that other electron is going to orient the magnetic moment the other direction. They will be equal opposites from that. And also from that, the magnetic fields of those 2 electrons will cancel out. So that's the other thing with it. So we do this, the spin up and spin down. And one of the things, now this is the Pauli exclusion principle. So Pauli exclusion principle says no 2 fermions, electrons are fermions, no 2 fermions can have the same set of quantum numbers in the same atom. So what does that mean? That means for each energy state, and I mean not including spin up and spin down because they have the last quantum numbers different, the spin's different, no 2 fermions or electrons which are fermions can have the same set of quantum numbers in the same atom. And now because of that, that means that electrons will only occupy specific orbitals. And the so what of this is the reason why matter has structure. So this is also the reason why light does not have structure. Well, the photons themselves may have structure. We don't know. But because I mean, what can we do? We can't slam light together and break it apart because they can occupy the same space at the same time. Whereas electrons and protons and nuclei, we can slam them together and break them apart and see what's inside them. So, but this is, like I said, this is why matter has structure. Now, the Pauli exclusion principle does not work for bosons, which have integer spin. So a fermion is a particle that has a fractional spin. Bosons have integer spins, and they do not follow the Pauli exclusion principle. So light, for instance, is a boson. It does not follow that. So for multi-electron atoms, they do not necessarily have the same energy. So because of electron shell interaction, so the inside shells can shield the other ones. So and because of this, there's some weird things. This is known as the Zeeman effect. So it has to do with the magnetic field. So when you have a hydrogen or a hydrogen-like atom, where you have a single electron, the all of the principal levels, they're known as degenerate, meaning they have the same energy. The second that a second electron appears, or a fermion if you're doing something like a muon, but I know anytime this happens, this is known as a Zeeman effect, where the magnetic field of the electrons then split the energy levels, and then the different types of orbitals, the S, P, D, F, and higher. We usually don't go higher in this class. They will then have different energy levels, and then you build them up by what's called the Aufbau principle. That's a German word that means building up. So here is the effect of the Zeeman effect, and this is for two or more electron atoms, and you can see that the where the ends, they in a hydrogen like would be degenerate, whereas the same energy, but then they split, and then you populate them then by the lowest energy first. So the reason, just like the analogy of the party of sitting in the chairs, right? So if you're the first one in the party, you pick the comfy lazy boy. If you're the second of the party, you pick the couch, and you occupy the couch until there's no seats. Then you sit in the chairs, and you do standing room, and then you personally pick the lowest energy first, because that's human nature, right? You want to try and be, if you're going to be somewhere for a while, you want to put as little effort to as possible. Electrons are the same way. Electrons are very much like people. So we can have, billion up, hydrogen's going to be spin up, and we just pick spin up because let's face it, chemists are very positive people. We like to be uplifting. So spin up, so the second one is equal opposite spin down. And now for the third one, billion up, we're going to put lithium is going to have an electron spin up in the 2s orbital, and then we keep on going. So beryllium is going to have 2 electrons in the 2s, boron is going to have 1 in the 2p. Now we get the carbon, and the other, now it becomes known as Hund's rule. The electrons occupy spin up in 2 different orbitals. And for me, myself, I like to swim. I like to swim laps. That's one of my things I like to do for exercise. And if I'm the first in the pool, I will take an open lane. And if that swimming pool has 3 lanes, and if I have an open lane and then someone jumps in the pool and then jumps into my lane, I'm going to be a little upset. I mean, I can still do it, but, why would you come in my lane when you have an open lane all to yourself? Then we can swim parallel to each other, and, then we can be happy. So that's what electrons do. They populate, just like with that, they have parallel spins, and humans swim at different speeds, but let's say, we're identical twins and we swim exactly the same. So we'll swim, parallel to each other, and then we can keep on going until this is filled, and then the second person can join the lane, and we'll swim at equal opposite. And electrons kind of go the same way. That's Hund's rule, and of course the when they occupy the empty orbitals, they will have their spins aligned parallel, and it's just because it's easier to align your magnetic field with something that's already got a magnetic field. So it's lower energy. You can do it the other way, but it's higher energy. And electrons are like people. They like to be lazy. So why would I be lazy when this is the easiest thing to do? So do parallel spins. And this shows you another way how to occupy the orbitals. And so how to write electron configurations. Put the lowest energy first, and when you have 2 electrons in the same orbital, they have to have opposing spin. This is not necessarily known as a Pauli exclusion principle. This is a side effect of the Pauli exclusion principle. And if there's degenerate energy level, same energy level, they will occupy each one singly by electrons, and they will do parallel spin. This is known as Hund's rule. So so here is some billion up. So now you've gone on after carbon comes nitrogen, and you filled up the extra electron will then go parallel spin to the p orbital. Now oxygen, the extra electron, will then go into one of the p orbitals with the other spin direction, and then it'll continue billion up to you get to neon. And now the second principal quantum shell has been filled. So let's look at sodium here. Sodium, then, the next highest energy orbital is a 3s, and there's one electron. And if you want, you can skip this by, instead of writing out the entire orbital configuration, you can put neons in brackets. You can only use a noble gas in brackets when you write electronic configurations. So you can't put another element in brackets, only noble gases. So helium, neon, argon, and so on. And let's talk about electrons. Valence electrons. These are outer electrons. These are ones that have the highest n. So it's the principal quantum number. The principal quantum number with the highest n, those are the only ones as valence. These are the outside. Electrons that are not in the principal quantum number, the quantum shell, are known as core electrons. So valence, remember that valence is only the highest number of n, and so this varies across the periodic table, and it's funny how consistent they can be. So for silicon, here's the electronic configuration for silicon. Silicon has 4 valence electrons because remember the superscripts imply how many electrons. It has so the n equals 3 is for the 3s and the 3p, and there's 4 on the outside, and then there's 10 on the inside. So there's only 4 valence, 4 outside. So now what about for other ones? So here is the electronic configuration for selenium, and it does have the 3d electrons all filled. And the 3d electrons are higher energy than the 4s, but the 4s is still the higher principal quantum number. Therefore, selenium has 6 valence electrons. It does not have 16 because the 10 electrons in the 3d orbital are still considered core. So keep this in mind. So now the periodic table, and this seems to make a lot of sense for the first 3 periods, and the periods are row. So you see the periodic table, the periods are row. The first 3 are described pretty easily and pretty well understood. Now the thing is, when you start getting the higher periods, it gets more complicated. So the first 2 groups, this is known as the s block, the s orbitals, and then the 6th group on the right is known as the p block. The transition metals, these are the d orbitals, and then the rare earths, these are known as the f block. So here, and this is how we organize the periodic table. And so the first 2 columns on the left, these are the s block elements, although helium is also, we put it with the noble gases. And you can see that hydrogen, helium are lifted off top. Then the orange area of the 6 columns on the right, those are the p block elements, and then you have the d block elements, and then on the bottom you have the lanthanides and the actinides, and you have all the structure here. And I was telling you about the billion-up principle, and I want you to understand that even though I told you some of these things, there are exceptions to the rules. So if you look here, if you look how these are being built up, and look at period number 4, for instance. So you have Potassium at 4s1, calcium 4s2. Then it looks pretty good. So scantium 4s2, D1, titanium D2, vanadium 3, chromium. What happened to 4? So it's 4s1 and now it's 3d5. Well, that's weird. Oh, manganese. Okay, that makes sense. Manganese, iron's good. Cobalt's good. Nickel's good. Copper. What? Went to 10. And zinc. Okay, we're going back to being normal. So and you can see and look at under nickel. So nickel there, and underneath palladium has 4d10. Like, what happened to the 5s? And then you go to platinum and it's S1d9. Like, what is going on here? So if you go and you do the quantum mechanical calculations and you do the crazy physics and you find out the lowest energy levels of all the magnetic fields of the nucleus of the different electrons and how they interact, that does tell you the lowest energy levels. So this class is just the beginning. This is much more complicated. I want you to understand that there are exceptions to the rules, that you don't have to understand the exceptions to the rules, but I want you to understand there are exceptions to the rules. And you can study this far more in detail in future classes. So, and you can also see, even if you look at the F block elements like the lanthanides and the actinides, you can even see that it can get even more complicated. So this is, for me, I think this is fun. This is where I think chemistry is cool. I like it that it's so complicated, and I like trying to figure it out. So this is the fun stuff. The general rule, why the exceptions? When you have complete shells, there tend to be a little bit more stability. That's why you can see that several times it'll jump up to a full shell of 10 for the Ds, and it just depends on the environment, whether or not when it goes to a full shell or a partial shell, and and it's not consistent, right? So it's kind of weird in that respect, but it's still, it's fascinating, and this is one of the reasons why I love chemistry. It's because it's complicated and fascinating. So. All right, let's go back, and the number of valence electrons for the main group element, and so this is the S's in the P block, and it's equal to the number in this column with the exception of helium, because helium only has 2. So for instance, chlorine has 7, and it's a halogen, so all halogens have 7. And then the row number is equal to its highest principal shell, the N value. And so for chlorine in row 3, its highest principal quantum number is equals 3 shell. And so that's important for bonding later. And also, even though chlorine, for instance, doesn't have any, in the ground state, have electrons in the d orbital, it has d orbitals. So it has them available for bonding and such. So electrons can be promoted into the d orbitals. So, the electronic configurations differ somewhat, but it really depends on the environment, and so it's more complicated, like I said. So it really just depends. And there's a couple of exceptions, and there's even more exceptions that you keep on going on. And for this, these exceptions, these are mostly because of the stability of having a full D shell. So I mean, for chromium having 3d5, this having one electron in each of the d orbitals is slightly lower energy than having 2 electrons in the s orbital and only 4 in the d. And same idea for copper. And you also know, I mean, copper, and below it is silver and gold. Copper, silver, gold are very unreactive atoms. So they this stability provides its nobility. Of course, it's not as noble as noble gases per se, but it does make the element rather unreactive. So we can use the periodic table to get a general idea. And let's look at the electron configuration of phosphorus. So if you look at this neon, so I'm going to start with neon's electron configuration, and then it goes to the 3, So it's going to be 3s squared because 2 electrons in the s, and then move over 3 spots, so 3p3. So that's going to be electron configuration for phosphorus based off of that. So you can move it over, and already aforementioned, you can use the noble gas configuration, and you can use the blocks going over to the right in that way. So remember, the highest principal quantum number is equal to the rho, and it doesn't necessarily mean that all of the different types of electrons will be there, but the outermost d electrons there is not necessarily in that spot. So, and the valence electrons, the outer electrons, these generally determine the chemistry, the reactivity, and the bonding that the electrons go to. And noble gases, these have very stable electronic configurations that are low energy. And so because of that, things tend to bond, so gain or lose electrons, and they do that through bonding or by ionization. They do this to approach the noble gas configuration, because it's a low energy, it's a very stable configuration. So this is the reason why things bond, and that tells us now how things are react. It'll tell us what things will react, what things won't react, who they will react with, how much they will react with. So this is the reason why it's such a powerful model. And for instance, the alkali metals tend to form +1 cations. Halogens tend to form -1 anions. And because they are the same structure as the noble gas configurations. So alkaline earth metals are reactive, but not nearly as reactive, because it takes a little more energy to rip 2 electrons off. It still takes energy to do this, but they're not as reactive. And noble gases, generally speaking, are relatively inert. They kind of just kind of sit there with their electron configurations and not really interact with anyone, because they're like, I'm already fulfilled. I'm low energy and I'm lazy. I don't need to work with the other people to be more lazy. I'm already lazy enough. So that is the reason why noble gases are so noble. They're so lazy. They're so unreactive. So here is then the prediction you can see with the periodic table, and they're organized in such a way that you can have various charges. And you can see then with the transition metals, as I mentioned, it's more complicated. And then there's various bonding schemes that can form. The electron orbitals can change depending on their environment. I mean, when they're by themselves, it's really easy, but when they bond, they interact with other nuclei, interact with other electrons, and then their energy levels change. So a new energy levels form, and then the rules change. So we're not going to go into this class. Future classes, you can learn all about that. Just know that they are there. So let's talk about periodic trends. This is a long chapter, geez. So as you move to the right across the periodic table, the atomic size decreases. So if you look at this, and look at the top numbers, and the 1, 2, 3 on over down to 8. So let's start off with hydrogen, and hydrogen has its outer shell and it has 1 proton. Helium has 2 protons, and it is still in the same shell. What happens is that second proton pulls the electron cloud closer to its nucleus, so helium is a smaller atom than hydrogen. So helium is in fact the smallest atom. Then on the next line here, lithium is actually a big atom. And then beryllium, spot number 2, is a smaller atom. Then moving right, boron is smaller, carbon smaller, nitrogen smaller, oxygen smaller, fluorine smaller, neon the smallest for period 2. So then now let's go up in the period. Let's look at on the noble gases. Helium is the smallest atom, then underneath that neon. So actually going down the periodic table, the atoms get bigger. So this is the general trend. So going to the right, it gets smaller, and going up, it gets smaller. Or Going to the left, it gets bigger. Going down, it gets bigger. So this is the periodic trend. And it has to do with its internal charge. So, and it's the same shell. So for each period, it's the same shell. So therefore, it causes, that's how it works with that, with the size of the nucleus. So this is the same as I've going on. Here's the picture. I guess I should have used this going on. So going across to the right, it gets bigger. Going across to the right, it gets smaller, and going up, it gets smaller, or going down gets bigger, and going to the left, it gets bigger. So, and now let's compare this to first ionization energy. So first ionization energy is going to be opposite. So let's look at two elements. Look at cesium, number 6 on the bottom, so CS, cesium, down on the left. And then let's look at neon, top right. Let's compare these two. So cesium is a big atom. It has a +1 sort of charge of its nucleus. And neon is a tiny atom with an electron and has a +8 charge. So now you want to rip that electron off. And remember, electrons are attracted to positive centers. So the electron in cesium, it's relatively easy to rip this off. It's got a +1 center, and the electron is further away. The further away the electron is, the less attractiveness it feels to the nucleus. Neon is a tiny atom. Its electron is really close, and it has a +8 center. And so because of that, it is much more difficult to rip that electron off. So the trends in first ionization energy is the exact opposite of size. So that means, and this is the first ionization, the energy takes to rip off the first electron. So the lowest first ionization energy is down and to the left, and the higher one is up and to the right. So equal opposite of size. So same idea here. And the element that has the highest first ionization energy is helium. Helium is the highest. And the lowest, as far as we can tell, is francium, but francium only exists for a very short period of time. It's so radioactive it falls apart really quickly. So I don't even know if we've experimentally measured that or not. We may have. So metallic character, I don't necessarily agree with this because I like to think in many absolutes. But metals tend to be the left and down. So the metallic trend tends to be down and to the left. So and it fits pretty well in the P block, but it doesn't necessarily work because like what is the best metal? Does the best metal conduct electricity the best? Does that mean cesium or francium is the best metal? The element that conducts electricity the best of the elements is silver. So is silver the best metal then? Not by this, So what is it? It's this works pretty well though for the P block. It doesn't necessarily work for all of the periodic table. And but if you look at the P block there, as you move down and to the left, the elements become more metallic-y-ish. And so kind of like you do see the transition then but it kind of makes sense if you compare carbon to fluorine. Because carbon can conduct electricity. It can also conduct heat very well in the diamond form, where fluorine doesn't really at all. So does that mean carbon is more metallic-like than fluorine? I guess so, kind of thing. So I never really liked this trend, but I think it is good for the P block, though, because it explains why carbon is a non-metal and lead is not. And lead is a metal, even though it's in the same family group as carbon. So that is kind of interesting. So to me, I think this fits best in the P block than the rest of the periodic table, because does that mean that francium is the absolute best metal? We can give the smallest atom to helium, that we can give that honor to it, but we can't say what the best metal is. If I had to pick a best metal, I'd pick silver because it conducts electricity the best. But hey, I'm not the one writing the book here, so but like I said, works pretty well for the P block. So here's the review. Ooh, long lecture. So here we've described light, electromagnetic radiation. We talked about the Bohr model. We talked about the quantum mechanical model. And this is just the beginning. And then the electronic configuration. I tried to fill in the pieces there. I know that we didn't talk about the magnetic moment as much. We only briefly talked about spin. This is a little more complicated. Hopefully, I know that this is beyond the book, but I want to try and have you understand where it comes from and where it builds up from. And then the periodic table, and it works mostly by configurations, by electronic configurations, and then predicting the chemical properties from these configurations. So that's really the power of the periodic tables. We're predicting chemical properties from that, not necessarily physical properties. And then the periodic trends, we've mentioned other things like the atomic size, ionization. So it works also for physical properties, right? So this is a reason why the periodic table the way it is, because it's so good at predicting properties, both chemical and physical. So it's a very powerful tool. So here are the learning objectives and the legal. And again, thank you for listening to this lecture.